Life Sciences, Lecture 2, The History of Western Science, Part 2. All right, so we looked at the history of Western Science, Part 2, which basically, in that we were looking at ancient Greece. So here we have the exact same objectives. We're just going to get a little farther into those. Excuse me. So in the first objective, we're going to move into the period of Newtonian physics, but we will still actually, we're starting in Aristotelian physics, and we will be there for quite a while still, and then moving into Newtonian physics. In the second objective there, we're getting into Archimedes, Copernicus, Galileo, Descartes, Newton, and Einstein, and their contributions. Okay, so let's get started. Let's reorient ourselves here to the Western, or the timeline of Western scientific thought. So we had started on the left looking at Hippocrates, Socrates, Plato, and Aristotle. We're picking up today, if we just move one little notch to the right, we're picking up now with Archimedes. So you can see that Archimedes lived in the 100s, so around 100 years before that magic non-existent year 0. So partly what that means is the time of his life was tumultuous. The things that were happening then were essentially ancient Greece was that civilization as being, Athens being kind of the center of the Western world there was beginning to fall apart, and Rome was becoming that sort of cultural and political center of the Western world. So so the Romans were coming to power, which means that, of course, again, there were wars. So when we were looking at for instance, Plato's time, the wars that were happening then were among Greeks. And now in Archimedes' time, what we're looking at is Romans coming in and taking over Greece. So, okay, so let's see what we have here. So our first scientist is Archimedes. Now, Archimedes is considered the greatest mathematician of ancient times. This is a man who, in his spare time, sat around with a compass, making circles, and then making triangles in those circles, and figuring out the surface of the triangles, so the surface area, so he could use that to figure out the surface area of the circles. So he is and then also he did that similar kind of work with spheres, like turned spheres into I like to credit him with the invention of a disco ball. And so what that means is he was the first in the Western world that we know of, to figure out the surface area and the volume of a sphere. And to figure out the surface area, he essentially turned the sphere into, hundreds of little squares and triangles, and figured out the surface area of those, and then extrapolated that into the sphere. So what does that mean? What did he discover? He discovered pi. He discovered that value that we use to figure out the surface area of circles, the circumference of circles, the circumference and surface area and volume of spheres. So this was, groundbreaking work that Archimedes did in mathematics and geometry. What else did he do? Physics, engineering, astronomy. I think in many ways we could call him the father of engineering, because he took these ideas, these things that he was discovering in mathematics, and turned them into real life usable tools. So one of the things that he created, here's his work with circles and spheres and volume and surface area and that kind of thing. This was, like it says in the notes, this would be considered the mathematical equivalent of the discovery of the world. I mean, sorry, not the world, the wheel. Just we didn't know before Archimedes. We didn't know how to calculate the area of a circle, for instance, or the volume of a sphere. But here's one of the things that he invented is called Archimedes' screw, and so this is like, kind of shows his engineering genius that he was using. And Archimedes screws are used today. What it is a spiral that is put down into water, and then when it's turned in the right direction, the water moves up the spiral. And so, this is practically magic, the technology that he created here. He found a way to make water run uphill. This was a thing that, before this, people were bringing water uphill and carrying it in buckets, or, something like that. So this is pretty amazing technology. He also figured out how to calculate levers. So, for instance, if there was a pivot point in the middle of a lever, and then we had the lever, like, say, a piece of wood, like a seesaw. Imagine a seesaw or a teeter-totter. So he figured out how to do calculations with that. Like, if there was a certain weight on one side, where would that fulcrum need to be, and or how much weight would you need to use on the other side to move the weight that was on the first side. And he actually then, the tumultuous warring times that he lived in, he used that kind of thing to make important war tools. So he lived in a town that was a port, which many places were ports, of course. In Greece, there's a lot of coastal area, and civilizations always have grown up around the ocean and other sources of water. And anyway, so he invented things like a lever that would be on land, that would extend into the water. So when enemy ships came into port, they could use this to hook onto a part of the enemy ship, and then use manpower on the other end of the lever to lift the ship up, swing it around, and slam it into the walls of the dock or of the port to destroy the enemy ships. So, like, how brilliant is that? Anyway, what Archimedes is probably best known for is his Eureka moment, and this statue, I love this one, this depicts Archimedes in his Eureka moment. His Eureka moment was, there's a whole story around it, and it is this, that the ruler of where he lived, the king, where he lived at the time, had a little problem. The king had commissioned a lovely gold crown, and so he gave a certain amount of gold to a goldsmith and said, please make this lovely, ornate, intricate gold crown for me. And the goldsmith did that. And this crown had leaves and swirls and vines, and it wasn't your basic, like, Burger King kind of crown. It was delicate and intricate and beautiful. So when the king got the crown back from the goldsmith, he had a sneaking suspicion that that the gold that he gave the goldsmith was not all there in the crown. He felt like the goldsmith kept some of that crown and gave him back, or kept some of the gold, gave him back a crown that was made up of less gold than what he had given him. But he didn't have a way to prove it. So he put Archimedes on the problem. He said, Archimedes, I want you to figure out how much gold is in this lovely new crown of mine, because I suspect it's less gold than I gave the goldsmith to work with. And Archimedes said, yes, sir, I'll get right on that. And he had no idea how he was going to figure that out, because the crown was so made up of shapes that were going to be impossible to measure, to calculate the volume or the surface area of the gold that was there. So he thought about it and thought about it and thought about it to try to figure out how he was going to calculate the amount of gold there, the volume of gold. And so in his process of thinking about it, he settled himself into a nice hot bath, which is one of his favorite thinking places. And as he observed the water rise up as he sat down into the bath, that was his Eureka moment. He realized that the volume of his body going into that water displaced the water a certain amount, and that we should be able to calculate the volume of the thing going into the water based on the amount of water that was displaced by that thing. And so as the story goes, he had this eureka and eureka means I've got it in Greek, and we still use that word today. But he, as the story goes, he jumped back out of the bath once he realized that this was how he was going to calculate the volume of gold in the crown, and went running through the streets, forgetting to dress himself, to go to the palace to tell the king that he figured out how to calculate the volume of gold in the crown. And as the story goes, we don't know all the details of what happened with him running through the streets naked and all that, but he did live to go on and do more great things after this. But he so anyway, they measured the crown. It did indeed have less gold in it than the king had given the goldsmith. So that goldsmith, of course, did not get away with cheating the king and keeping some of the gold for himself. So I'm sure he came to a swift and potentially unpleasant end. But as a result, we now have the Archimedes principle. So again, what Archimedes' principle is when we lower an object into a container of water, the object displaces water, which flows into a smaller container. This is when we're all set up to do this experiment and measure it really nicely. And so then when the object is completely submerged, the volume of the displaced water equals the volume of the object. That's Archimedes' principle. Okay. So Archimedes' death happened when, let me look at my notes here. We don't have his death, but somebody knows, but I don't have it in the notes. He was born in 287 BC. So but he did die, and he died in a way that wasn't ideal, and no one really meant for it to happen that way. So what happened was the Romans were invading where he lived, and they knew full well that Archimedes lived there, and they knew full well that he would be valuable to them for the inventions that he made, for his contributions, etc. So the invading soldiers had very strict orders, and when they invaded, this was not like war, like, oh, we're just going to fight between the soldiers. They invaded, and they went through the town, and they killed everyone that they saw. That was what invasion looked like. And so the Romans invaded. Archimedes was at home working on circles when soldiers burst into his house. The soldiers were given strict orders not to kill Archimedes, to capture him. The Romans wanted him to be able to make things, for them. But something happened. The soldiers didn't know who they were looking at, or something like that, and they did kill Archimedes. His last words were said to be, "Don't disturb the circles." He had circles all drawn out, and he was doing something with circles, and he didn't want them disturbed. But and maybe the circles weren't disturbed, but that was the end of Archimedes' life. So that takes us then we had the rise of the Roman Empire, and then the fall of the Roman Empire happened at 410 Common Era. So then we have the Middle Ages that were from 410 Common Era to 1500. So 410 is the fall of the Roman Empire. That strange year 0 is the beginning of the Roman Empire, and 410 is the end of it. So from 410 Common Era to 1500 Common Era, we have crickets chirping in the scientific world. Nothing happening at all. Now, but let me say something about that. So those are considered the Middle Ages, that span of time, which is about 1,000 years. So in the Middle Ages, it is said that during this time there were numerous wars over religious beliefs, and land and resources, etc. Advances in science, mathematics, art, and philosophy were essentially non-existent during this time. However, so that's the narrative that's taught, that the Middle Ages happened during this time. But let me say this, that there are historians at work today. One of them is a Russian historian by the name of Fomenko or something like that. I'm probably not saying his name right, but something like that, Fomenko, or I don't know. Anyway, and they're re-examining the timeline that is taught to everyone throughout recent time. And because what he's and the historians he's working with are finding is that they're finding that what Winston Churchill said was true, is that history is written by the victors. And so sometimes what happens is the victors want to create more space, or actually more time, between their time and the previous time. And so sometimes hundreds of years are inserted into, like in the timeline. So so we can look at records of different ruling families, and we can say there was this person, this was here's another person, this was their child, this person ruled for this long. But then we'll see that whole scenario of those parents and that child and this ruler, etc., repeat itself 200 years later. And so these historians are re-examining things and going back to source evidence, and saying, hey, guess what? Maybe there wasn't actually 1,000 years between the fall of the Roman Empire and then the beginning of the Renaissance. Maybe there was many fewer hundred years in between there, but we were just kind of creating some space between ancient times and modern times to make modern times more modern. Like, that's kind of the idea of what was going on there. Like, give us more space from these decrepit old ancient ideas, and now we're so innovative and new and whatever. Anyway, so that's a thought that that rattles around the history world. But anyway, back to the Middle Ages. So Middle Ages were coming to an end. And so anyway, we have all this time that there's nothing to say about what was happening scientifically in the world. And that was the Middle Ages. But now on to Copernicus. So this is Copernicus. And notice what he's drawing there. He has a series of circles on the paper that he's working with. And what that is his heliocentric model of the known universe. And that's what Copernicus is known for. So Copernicus was a Polish-born mathematician and astronomer. And let's see, what else did he study? Politics, literature, philosophy, etc. So notice that his time frame, he was born in the late 1700s and died in the mid 1500s. So if we zoom back to our timeline here, we notice that that the Renaissance time, so looking at the blue across the top, we have the ancient world on the left. We have the Middle Ages, that's about 500 to 1500. And then if we go to the right one more, we have the Renaissance, that's the 1500s to the 1700s. So the beginning of the Renaissance, it didn't start with a bang. It started very gradually, and Copernicus was key in the beginning of it. So you can see that his death date is 1543. So 1543, seems like a good time to get rolling with the Renaissance. However, the political climate at the time was such that it was not at all safe, if you valued your life, to speak out against the church. So of course saying, whatever the church believed, that, God is God, whatever. You couldn't say anything against that. But the church had clear ideas, political ideas, scientific ideas, etc., that, that was like the word of God, essentially. And you could not say anything against it. You could not refute it in any way if you wanted to live. And so, however, Copernicus quietly did his work. So in the early 1500s, work like his was done quietly because studying science was not something that the church wanted happening, because the church was all powerful and wanted to stay that way. But he figured out a way to kind of cheat that system, the system being, if you speak out against the church, you'll lose your life. So what he did was he made his calculations. He had his theories, he made his observations, he made his calculations, and he said, I am certain that we are living in a heliocentric solar system. They didn't really actually have the idea of solar system. That was the entire known universe at the time. And so what he did was he recorded his calculations. He drew everything out, made it very clear for anybody who understood math and astronomy, etc., to look at it, to check his numbers, etc. He had it all ready, and he did not come out with his ideas until he was on his deathbed. And so once he died, then his work was published, and at that point, then there was no one alive for the church to kill for speaking out against their beliefs. And so in doing that, that was his sort of genius last stand that he took against the church, because if they didn't have someone to kill to say, oh, look at his stupid ideas speaking out against the church, that allowed his ideas to stand, and it worked. And other scientists then got to read his work, and that was a key beginning of the scientific revolution. That was part of the Renaissance. So Copernicus was in Poland. Our next person we're looking at is Galileo. He lived in Italy. So Galileo was on the heels of Copernicus. So Copernicus died in 1543. Galileo was born in 1564. So Copernicus's ideas were circulating around Europe when Galileo was a young man, and he was fascinated by his ideas, and he looked at Copernicus's calculations and said, by golly, I think he's right. And so part of what Galileo did was he did some fantastic development of lenses so that he could build a telescope far more powerful than any telescope that had yet been developed. And back in those days when it was nighttime, it was dark out, and you could see the stars and the planets really quite well. And so with his powerful telescope that he developed, he made all sorts of observations of the night sky that hadn't yet been made, because his was the most powerful telescope at the time. Now, during Galileo's time, it was still unwise to speak out against the church, but you weren't necessarily going to die for it the way you were in Copernicus's time. So Galileo, one of the key things that he did was he confirmed Copernicus's calculations and said, yes, we do live in a heliocentric solar system or universe. So let's see. So he supported that theory, and he did lots of other things. Like I said, he developed he advanced the development of lenses and the telescope, so which really advanced the field of astronomy. But with that, he discovered Jupiter's moon. So one of Jupiter's moons is named Galileo, after Galileo Galilei. And so he was able to basically, you can't see Jupiter's moons, but he was able to observe Jupiter closely enough to observe that there must be a sizable body going around Jupiter because of changes that he was able to measure in Jupiter's orbit. So let's see. But big contributions from Galileo. Oh, here's what I was going to say about him. That he confirmed Copernicus's ideas. And for this and other things that he did, since it was now not necessarily so popular to kill somebody for speaking out against the church, but the church still didn't like it, he spent a whole heck of a lot of his life on house arrest. And so, which he did okay with, being on house arrest. He had his telescope, he had a lovely house, and so he made his observations of the night sky, and he made his calculations and did lots of contributions from, while being on house arrest. But when he wasn't on arrest, the kinds of things that he was up to were, for instance, like this. So what this is depicting is Galileo dropping 2 balls from the Leaning Tower of Pisa. So why did he do that? So he did that and lots of other things because Galileo was key in beginning to question Aristotelian physics. So Aristotelian physics that started way back in ancient Greece in what was it, maybe 300, 400 before Common Era, and now we're in the 1500s of Common Era. That is still what was being taught in universities. So, it was alive and well, and the rhetoric being taught for 2,000 years. And finally, here comes Galileo, and he's questioning it. And so remember that Aristotelian physics was based on those 4 ideas of impetus and natural place and force, I think was one, and what was the other one? Something else. It escapes me at the moment. But anyway, so what Galileo looked at, so for instance, Aristotelian physics held that if you dropped 2 masses of the same material, but one was larger than the other, that the larger one would fall faster. That was and so, when you think about that, that sort of intuitively makes sense that if you had 2 bricks, for instance, or 2 balls, like we see here, and they were both made of the same material, one's bigger, one's smaller, that the bigger, heavier one would fall faster. So, but Galileo said, well, does it really? And so he took 2 balls of the same material up the Leaning Tower of Pisa, and he dropped them. And what he found was they fall at the same rate. And not only did he do that, he asked other people to do it. So he recorded very closely the things that he did and how he did them and what he used, so that his experiments that he did could be replicated by other people around the world. And he asked people to do that. And they did. And this was the beginning of not necessarily the scientific method, but yeah, I guess it was the beginning of the scientific method and the beginning of scientific research as it is still done today, where we try to carefully record what we do and plan what we're doing and have it all set up in a way that anybody at any time at any place should be able to, with the right materials, replicate that experiment, and they should be able to get the same results. So the more that certain things anything was replicated, and the more same results we got, the stronger that upheld the theory, whatever theory that was testing. So this was one way in which he began to question Aristotelian physics, and so he did lots and lots of these things. So Galileo was key in sort of putting to rest a lot of Aristotelian ideas in physics, which then kind of created the space for some new physics to be discovered and worked with, and that kind of thing. So let's see. Oh, one other key contribution of Galileo. He did lots and lots, but he actually was the first to come up with this idea of relativity. So, we know that Einstein is credited with the theory of relativity, but Galileo was actually the first to observe it. And so what we're looking at here is one boat traveling across water. So it's moving through time and space. And so imagine, so you see that blue ball. So what he observed is that if somebody climbed up the mast of that ship and they had a ball or something up there, and that ship was moving along. The wind was blowing. The ship was moving, across the water. The person up on the top of the mast with the ball, if they dropped the ball, what they would observe is the ball falling straight down and hitting the deck directly below the mast, like right at the base of the mast of the ship. So that was what the person on the ship would observe, and anybody on the ship would observe that, the ball falling straight down the mast and hitting the deck right below where it was dropped. Someone on shore observing the same thing would observe the movement of the boat across, through space and time, and when the ball was dropped, they would observe an arc that the ball traveled, so that the ball would catch up with the moving ship and hit the deck right there at the base of the mast. So the person seeing it happen on shore would observe an arc to the movement of the ball. Anybody on the ship would observe the ball falling straight down. And so this idea is relativity. What that means is that that what an observer observes is based on their vantage point, and different observers are going to observe different things. So anybody on the ship is within that kind of realm of relativity of the ship. And so the movement of the ship through space and time, everyone on that ship and everything that happens on that ship is all as if it is not moving. Whereas if you're at a different vantage point and you see the ship moving through space and time, then you're going to observe things on that ship differently from that different vantage point. And the idea of relativity is that the observers in those two vantage points are both correct. That on the ship, the ball does fall straight down, and on the shore, observing it from the shore, the ball does fall at an arc. That is sort of one of the key ideas of relativity, that things appear different for different observers. And both observers are correct. So Galileo was the first to kind of bring those ideas forward in the world of physics, and then it wasn't going to be till like 200 years later that Einstein picked up where Galileo left off with relativity and completely developed that theory. Okay, so more Renaissance guys. We move on to the French philosopher René Descartes. René Descartes is known for his kind of key idea, cogito ergo sum. What that means is I think, therefore I am, or I think, therefore I exist. So in his thinking of philosophy and thinking of existence and reality and that kind of thing, he essentially applies Socratic ideas and questions to whittle down to, what do I know? What can I know? What do I know for sure, without, beyond a shadow of a doubt, is real, is reality? And that's what he came up with. He can observe that he's thinking. He knows that there is someone in him who is thinking, and therefore that thinking, because of that ability to think, he must exist. So that's where I think, therefore I am comes from. But what Descartes gave to the Renaissance was a very important thing. He gave the Renaissance a dualistic view of the universe. He essentially divided the universe into the material world, the things that we can observe, we can see, feel, touch, measure, etc., that observable world, and the immaterial world. So the material world and the immaterial world. So the immaterial world is things like like thoughts and feelings and ideas around God, and the unmoved mover, these things that are, or even like emotions and things like that. Those are all things that were considered part of that immaterial world. And so Descartes is lived from 1596 to 1650. So this is still, earlier Renaissance time where the artists and the scientists that were happily, busily, enjoying this revolution in art and science and literature and all of this, it still was sort of slowly getting going in Descartes' time. But his idea of this dualistic universe, or this dualistic idea of reality, kind of liberated the scientists in a key way. By having this delineation between the material world and the immaterial world, what that did was that kind of gave science permission to let the material world be their playground. And so anything that we could observe, we could see, feel, touch, taste, etc., and measure and all of that. And we could create experiments around, and we could have other people replicate those experiments, etc. That was all part of the material world, and that became the playground of the scientists. That's what they were allowed to work with. Whereas the immaterial world became the realm of the church. And so as long as the scientists didn't touch that, then they were safe, essentially, from prosecution by the church. So one of the things that I think is key, we all here are looking at Western science from this vantage point of Westerners, but we are Westerners here studying Chinese medicine. And so Descartes' piece here is key, because what he's doing here is separating the observable world from the world, or the measurable, palpable world, from things that are immaterial. And this was a break that never happened in ancient China, or more modern day China. So in China, we can look at various sorts of things that were happening through time, through Chinese history. But what never happened was, okay, there are these two parts of the universe, and part of it is material and part of it's immaterial. So immaterial, what we might call qi, that always stayed part of what scientists could explore and observe and work with. And so Chinese medicine then grew up around that, having qi be a thing that was part of their medicine. Whereas we can see here that Western medicine is part of Western science, and is evolving from this place that only the observable things are within the realm of science. So that's an important thing that happened in Western history, Western scientific history. Okay, so Descartes' dualistic view of the universe liberated scientists so that they were more free to observe and measure and whatever, and not fear prosecution. And so that brings us to Sir Isaac Newton, who was not a sir probably at the time yet of this painting, but he was the first person to be knighted for his mathematical achievements. So, which is why he is Sir Isaac Newton. He lived from 1642 to 1727. Now, Newton was said to be kind of an odd duck. He was obsessed with his work and not so interested in, social life and, hanging out and this and that. He really just wanted to work and work and work all the time. And so, which is partly why he had major contributions, and lots and lots and lots of them. So he continued Galileo's work. He, as far as astronomy and observing the night sky, and work with lenses and light. And so one of the things that he discovered is that white light, that within white light is the full spectrum of all the colors of light. So he, used prisms to show that from white light you get the whole rainbow, all of the colors of light. And so that white light contains all the other fields. So all the other colors. So he furthered the field of spectroscopy, and let's see, what else did he do? And he did, like he would gaze, he practically blinded himself. He would gaze at the setting sun for as long as he could to try to get at understanding what light was. And it would be a couple hundred years later when Einstein came along that when he began to then really create more set theories around lights and like what light was and photons and that kind of thing. So let's see. Newton, what else did Newton do for us? So Newton was a physicist. He actually also was an alchemist. And so as an alchemist, alchemists were really the beginning of chemistry. Up until this time, we couldn't really, chemistry wasn't so much a science, and yet it here in the 1700s and then into the 1800s is really when chemistry became a full-fledged science of its own, that we had the equipment needed to do experiments and make observations on a chemical level. But alchemists were the early chemists, but alchemists were doing things like trying to purify things, trying to make gold out of lead, which, unless there's magic involved, as far as we know, that's not something that can happen unless you're really able to manipulate protons and neutrons and electrons. But anyway, so he was an early chemist in a sense, in being an alchemist. But his quest, he was so even though he was a scientist and he was dedicated to science and he worked all the time and worked very hard, and left us with tremendous contributions, he considered himself very much to be a man of God, and in that, so he didn't really like that. He liked the dualistic view of the universe that was kind of the standard at the time, because it allowed him to study science in such a dedicated way. But he didn't really like the idea of God getting pushed out of science. He felt like God was part of the natural world, and his studying of the natural world, so much of it was his quest to find God. He felt like if he studied the natural world closely enough, he would be able to find that unmoved mover. He would be able to find the creator, the thinker who thought all of this into existence, and that is what drove a whole lot of his work, was his dedication to God. Now he taught at Trinity, and so he didn't actually uphold. So even though he was a man of God, he wasn't. I think he wasn't like key with the idea of the Father, the Son, and the Holy Ghost. But he was very much a spiritual man. Okay, so let's see what else. Oh, okay, so Newton, of course. What are his big contributions? Well, it's the apple tree, right? Okay, so Newton was around during the Black Plague, and he was there at Trinity during that time. And, and the plague was a pandemic that was, a for real, no joke pandemic. And so everyone was sent home to shelter in place, to, quarantine themselves to wait out the Black Plague so that, so that it wouldn't kill more people than it already had, etc. So he was home at his, whatever you call it. I don't know. It's not a farm. It's not a ranch. It's his estate, whatever. During the Black Plague, he was not there at work at Trinity College, and so which is why he was home, which is why he was sitting under the apple tree on his land there, and which is why then he observed an apple falling from the tree, as the story goes. And so that was his eureka moment, but he didn't eureka in Greek the way Archimedes did, but observing the apple fall gave him a chance, or sparked in him this, like, why do things fall to the earth? What is going on with that? And 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 as many of us have observed, being in quarantine, we kind of have more time to kick around ideas, and this is what came out of Newton's quarantine, is his universal law of gravitation, and also his 3 laws of motion, which are some of the biggest contributions that we have from Newton, although we have lots and lots of contributions from Isaac Newton. So let's see. So here's what's really, to me, amazing, incredible, cool about his law of gravity and his laws of motion. Here are his laws of motion. Is that if we look at his laws of motion, let's go ahead and read these. So law 1 is a body at rest will remain at rest, and a body in motion will remain in motion unless it's acted on by an external force. The second law of motion is the force acting on an object is equal to the mass of that object times its acceleration. In other words, force equals mass times acceleration. It's often stated just as an equation like that. Force equals mass times acceleration. And his third law is for every action, there's an equal and opposite reaction. So these are things that we've all learned in high school, and we've learned them probably on Schoolhouse Rock and whatever. They've been around our whole lives, and they explain the physical world as we can observe it. The thing about, and so to us, they're like, oh yeah, the 3 laws, like that's foundational, that's elementary, that's easy peasy. But what's really cool about it is really, to have these ideas, he had to be able to think outside of the box of gravity. So and essentially think outside of the box of what our reality is. So we live in this reality of our observable universe, and things happen in a certain way in that. So in other words, things are always acted on by gravity. And so anything that we see, that we can set something down on a table or that we can, roll a ball and eventually it will stop. These things are, everything is always being acted on by gravity. And so what we don't ever observe, unless we're in outer space, which certainly in Newton's time, that was not even remotely considered, what we don't ever observe is how things move when they're not being acted on by gravity. So he came up with this law of gravity. So that was his first one. The law of gravity, I don't have it here exactly what it states word for word, but the idea of it is that everything is exerting a pull on everything else, and the more massive a thing, the more massive the pull it creates. So in other words, the larger the gravitational field is that it creates. And so he used this to explain how the universe doesn't fall apart, that everything is attracted to everything else, and it holds the entire universe together. Now, Einstein would go on and essentially disprove this Newton's theory of gravity, but or embellish upon it, advance the idea, that maybe is a better way of saying it, but. So if for Newton to observe gravity and to understand that everything in our observable world is always being acted on by gravity, that was his key first thing to think about, to then be able to think outside that box. So, to me, it blows my mind. I can't think about thinking outside of my observable world in such a way that I would be able to accurately imagine how things would behave if they weren't being acted on by gravity. So that's to me, that's a huge contribution that Newton made, that he, number one, observed gravity, and then number two, came up with his laws of motion, which really explain how things would move when acted on by gravity or when not acted on by gravity. So his first law, a body at rest will remain at rest, and a body in motion will remain in motion unless it's acted on by an external force. So that is something that we can observe when something is not being acted on by any force. So again, if we're in outer space and there's no gravitational pull, or a very limited gravitational pull on something, we can see that we could take something and just have it hover and remain at rest, and then we can put some force on it, and then it will remain in motion, and it will keep going in that same direction at that same speed forever, until or unless it's acted on by some other external force. And so anyway, so his laws are key and are used still today. They're in the world, in the aspect of physics that it's called mechanistic what? Let's see, Newton's physics are mechanic. Oh my gosh, I forget. But it'll be in not the next lecture, but the next one after that, when we get into physics more. And so anyway, so we use Newton's laws for our day-to-day observable universe stuff. So for living in the physical world, Newton's laws completely apply. So for building bridges, for building buildings, for calculating how much force we need to exert on something, to get it to move, or whatever, that kind of thing. Newton's laws are still used today for that. We also still use Newton's laws or Newton's model of the atom, which has been unseated and is now not the accepted model of the atom, but in a lot of ways it's helpful and accurate, and we still use it in certain settings. And in fact, when we look at chemistry, we are going to use Newton's model of the atom. Okay, so let's move on. We're almost done here. So anything else about Newton? No. That takes us to Einstein. So we have a jump now and so there were lots of other people in between and so many other contributors during the Renaissance, and so many contributors like in the world of chemistry and microbiology. These were new fields that were emerging in the 1800s, post-Renaissance, as science was continuing. So like microscopes were developed as lenses continued to be developed more and more. And so science marched on in ways that it will, scientists continuing to discover things, and that brings us actually to Albert Einstein. So Einstein lived from 1879 to 1955. So his death date is in the 1900s. So many of us were alive and well in the 1900s, and so he's our pretty modern day guy. And since him there have been other massive minds in the world of physics, but Einstein was a theoretical physicist, and he was born in Germany and moved from Germany to Switzerland in the late 1800s, and became a citizen there and renounced his German citizenship. He would later return. So anyway, he lived and worked in Switzerland for a good number of years. He worked at the Swiss Patent Office. He was having a hard time in his early 20s finding work. He finally found work at the Swiss Patent Office, and he had a year while working there when he was just 26 years old that he called his miracle year. And one of the things that's really endearing to me about Einstein is that he had a practice of gratitude, that he observed the world, and the observations he was making were observations that were, like Newton's. They were so outside the box of the observable world that, but what Einstein said was that he observed the world and he had gratitude about that, and so the universe opened up and revealed itself to him, and it revealed itself to him in really amazing ways. And so similarly, how Newton was able to think outside of the box of gravity and come up with his amazing ideas, Einstein was able to think outside of the box of time and come up with, how what is time, what is space, what is light, what is gravity, all of these kinds of things. And he observed microscopic things in the world, and he observed macroscopic things in the world. So like, massive gravitational fields like that planets create, but also He explored photons and electrons, and this microscopic world that was not yet observable at the time that he was observing it in his own sort of internal way. So in his miracle year, he published 4 groundbreaking papers, and I can't say a lot about them. Once we get into Einstein, he's just beyond me, honestly. But his first paper was about the photoelectric effect, which had to do with showing that electrons bounce off or come out of things when light, a form of radiation hits them. So radiation, such as in the form of light, when it hits something, that electrons come out of that something. That's the photoelectric effect. His second paper explained the Brownian motion, which is a motion of, let's see, if you have something in solution, it's the movement that an atom, I think it's an atom, maybe it's smaller than that, will make in a solution as it's bouncing off of the molecules that are in that solution. Something like that is the Brownian motion. His third paper of that year was on special relativity, so that was his deeper development of relativity, which has to do with that everything that we observe depends on our vantage point in space and time, and that all observers are correct in their different observation of movement and time based on their vantage point. And based on how space and time is impacting them, they'll observe things differently. We'll watch a video on that, and it'll be explained so much better than I can explain it. His fourth paper was his famous energy mass equivalence. That is where his most famous formula, E = mc squared, comes from. E being energy, so E equals, or energy, the energy of the universe equals mc squared, which is the mass of the universe times the speed of light. And so what he's saying with that is that matter and energy balance each other always, that matter and energy are neither created nor destroyed, but they can change form, and they can change form to and from each other. And so what does that mean? Well, we'll look more at what that means. But anyway, so that's a key. Those are some really key contributions. So basically, Einstein developed quantum physics, which and now again we'll look, when we start to get into our physics section, we'll look at the 4 fields of physics, and there is more than one field of quantum physics. And so, but anyway, Einstein essentially is the father of quantum physics, and so he understood and studied and taught about nuclear fission, for instance, and advanced that field considerably, so that we were able to harness that energy that's released through nuclear fission, and create nuclear power plants that power many cities around the world today. So at the beginning of World War II, he endorsed a letter to President Roosevelt saying, hey, let me say this. He was working at the Swiss Patent Office when he wrote these 4 groundbreaking papers. That earned him a PhD at where do I have it in the notes? The University of Zurich. He later then went on to teach at a university in Berlin. So he did go back to Germany and taught for almost 20 years theoretical physics in Germany. In 1933, he happened to be, purposefully or whatever, was visiting the United States when Hitler took power in Germany. And so he said, I think I'm not going to go back to Germany, actually. Einstein is Jewish, and he felt like Germany was not such a safe place for him, which was a wise move on his part. And So he stayed in the U.S. and in 1940 got his U.S. citizenship and lived out the rest of his life living and teaching in the U.S. And what? Oh, so therefore, at the beginning of World War II, he endorsed a letter to President Roosevelt saying, "Hey, this is the kind of thing that they're developing in Germany right now. German scientists are studying and developing the ideas of nuclear fission, and they're putting that into a bomb, essentially. So, the German physicists were developing the first nuclear bomb. And so he let President Roosevelt know that that was happening, and so maybe the U.S. should do something as well. However, and so that did begin the Manhattan Project, where a number of top physicists in the U.S. Worked on that and developed the atomic bomb. However, Einstein refused to work on it. He felt like nuclear fission should not be used as a weapon, and one of his quotes around that he's famous for is something like that one cannot simultaneously prepare for war and peace at the same time. I don't know, so that's not a word for word quote, but basically the idea is that he felt like if you were preparing for war, you could expect the inevitability of war, and if you were preparing for peace, you could expect the inevitability of peace, and that was his preference. So, all right, what else? So, Einstein, our last little piece on Einstein. I think that's about it, actually. But his contributions, we know, like if you call someone an Einstein, or you say, wow, that kid's an Einstein, Einstein's name is synonymous with genius, so his contributions are enormous and still being used today. And we have all kinds of technology, like right there in your hand or in your pocket, your phone. The kind of technology that's used there is stuff that we couldn't have done pre-Einstein. His breakthroughs and contributions and mathematical discoveries allow us to do things like use GPS and use satellites and stuff like that. Because when we communicate with satellites from the Earth, we have to account for the fact that the satellite is moving very quickly. And so time is happening differently on the satellite than it is here on Earth, and so we have to accommodate for that in our equations. Otherwise, pretty soon our calculations are off as far as timing with the satellite, but also distance issues and that kind of thing. So anyway, so now we have totally common day-to-day technologies that we enjoy all the time that we can give thanks to Einstein for. Okay, let's take a look at what our homework is. Let's see, our objectives. Did we do all these? Heck yes, we did, because we rock. So we looked at, on the timeline, we looked at the ancient world, we looked at the Middle Ages. That was our cricket chirping. We looked at the Renaissance, all the stuff that happened in the Renaissance, and brought it up to the modern world, which essentially is Einstein. And we looked at that big span of time of Aristotelian physics and the period of Newtonian physics, which we are still in a lot of ways, but also we now have quantum physics as well. Let's see, and we looked at all of these contributors today, or not all of them. Last video we looked at Socrates, Plato, Aristotle, and Hippocrates. This video we looked at Archimedes, Copernicus, Galileo, Descartes, Newton, and Einstein. And we talked about their contributions. So, homework. So what I would like you to do is state one or two contributions of each of the scientists discussed in today's lectures. So I say today's, it's this hour. So you had a previous hour, and now this lecture too is the next hour. Archimedes, Copernicus, Galileo, Descartes, Newton, and Einstein. So one or two contributions of each of them. And this can be brief, like Archimedes discovered pi, Copernicus proved the heliocentric model of the universe. Galileo confirmed that, whatever. So, I'm not trying to do your homework for you, but there it is. It can be brief. And then the second one is, in your opinion, whose work was most revolutionary, and explain why you hold that opinion. Okay, so that's it for this lecture. Next lecture, we are getting into the scientific method. It should be a shorter lecture, and we'll kind of bring these ideas into, how do we use them today in using the scientific method. Okay, I will catch up with you on the next video. Hope this was enlightening, and I'll see you around.